So, integrating analytic functions. This section gives some very important results on which the calculus of residues is based. We start off with a simple example, really just to see what we actually mean by integrating functions. So what we want to do in this example is integrate the function f of z equals z, the simplest function just about you could think of, around a triangle, this triangle here. So it's a contour integral, we call it a contour integral. This is the sort of standard notation. So we have an integral sign with a circle to represent the fact that we're integrating around a closed loop. The gamma is a label for the whole loop, so this gamma really applies to the whole triangle and tells us, just labels the path we're integrating around. So what do we actually mean by this this contour integral? Well, basically we can divide it in this case into 3 steps, just the 3 sides of the triangle. So we're integrating from O to A, from A to B, and from B back to O. Now, as usual, writing z equals x plus I y, where this is the x-axis, is the y-axis. Differentiating this, we get dz equals dx plus I dy, and then we can simply substitute these expressions into these integrals. So z equals x plus iy and dz equals dx plus I dy. And what does that give us? Well, the first 2 integrals, which were from O to A and A to B, well, the first one was along here, obviously y is 0 and dy is 0. So we just end up with z equals x and dz equals dx. And x varies from 0 to 1. So we have this integral, the integral of z dz from 0 to a. Then up here from a to b, what happens? Well, then x is 1, and so we've got z equals 1 plus iy, and dz is simply, there's no change in x, so dz is simply I dy. So we multiply by I dy. Multiplying this out, what do we get? Well, it's I minus y dy. Okay, so if we actually do these integrals, well, okay, the first one is fairly trivial. If we integrate x, you get half x squared. Between the limits, you just get half. Integrating, well, you've got a constant here, so it's I, you're integrating a constant I dy. That just gives you I times y, and then you evaluate between the limits 1 and 0, that just gives you I. And you've also got minus y dy, so that gives you minus a half y squared. Evaluated between limits, you got minus a half. So overall, we end up with I, the integral from here to here. Then finally, to evaluate this last integral from b to o, the simplest way to do it is now to write z as r times e to the I theta, write z in polar form. Then you've got dz is equal to differentiating. Well, theta is constant, okay, and theta obviously is just 45 degrees or pi by 4. So it's just e to the I theta times dr. So dz is given by this. So just substitute in. So for the integral from O to B, from B to O, the integral from B to O is minus the integral from O to B, and the integral from minus O to B is, well, now we've changed variables to dr. So r now varies from 0 to the length of this line here, which is obviously root 2. So that's why I've got 0 and root 2 here. The complex number itself, z, is just r times e to the I pi by 4, which is this thing here. And then we've got dz, which is e to the I pi by 4 dr. So these two things multiply together to give you e to the I pi by 2, which is equal to I. So we've got I, which we can take out if we like. We've got minus I, and then we've got r integrated with respect to r gives us half r squared. Putting in the limit, we end up with half times root 2 squared, which is 1. So we end up with minus I. So finally, the integral we want is this plus this plus this, and we end up with I minus I, which is 0. Now, in fact, we would get 0 if we integrated f of z equals z around any closed loop, not just this triangle. And this is because of something called Cauchy's theorem.